Morning chemistry. Today we are going to talk about what is solutions, and we are also going to, or simultaneously, be beginning the last chapter that we will do this year. So we've almost made it. So let's talk about solutions. There are solutions all around you, but there are even solutions inside of you. You and all other organisms composed of cells containing solutions that support life. You inhale a solution when you breathe. You're immersed in a solution whether you're standing in a room or swimming in a pool. Structures such as the one shown in the pictures on the previous page, which would be 452, would not be possible without steel, and steel is a solution. So, cell solutions, ocean water, and steel might appear like they're very different things, but they share certain characteristics. So in chapter 3, you learned that a solution is a homogeneous mixture containing two or more substances called the solute and the solvent. The solute is the substance that dissolves in the solvent. When you look at a solution, it's not possible to distinguish the solute from the solvent because it's homogeneous. Okay? A solution may exist as a gas or liquid or a solid depending on the state of the solvent. Air is a gaseous solution. Its solvent is nitric gas. Braces may be made of nitinol, a solution made of titanium in nickel. Most solutions, however, are liquids. So you learn in chapter 10 that reactions can take place in aqueous solutions, so solutions in which reactants and products are mixed in water. In fact, water is the most common solvent among liquid solutions. So there's a table on page 454 called table 15.1, and it lists some examples of different types of solutions. Note that the solutes in the solutions might be gases, liquids, or solids. Which solutions contain gaseous solids? So looking through, you've got your solutes might be oxygen, carbon dioxide, oxygen gas, things like that. You've got some solutions that are aqueous. Aqueous is whenever your solvent is water. So now some combinations of substances readily form in solutions and others don't. A substance that dissolves in a solvent is said to be soluble in that solvent. So a substance that dissolves is soluble. Gotta make sure I spell it right. For example, sugar is soluble in water, right? You can dissolve sugar into different beverages. So you put sugar in your coffee or your tea. A substance that does not dissolve in a solvent is said to be insoluble. So sand is insoluble in water. Have you ever shaken a bottle of oil and vinegar? Oil is insoluble. And oil and vinegar are said to be immiscible. So that means that as soon as you stop, they mix. Okay, so two liquids that are soluble are miscible. So soluble versus insoluble. And then you also have two substances can be miscible and immiscible. That's if one can dissolve completely. So let's talk about solvation in aqueous solutions. So why are substances soluble in one another while others aren't? To form a solution, solute particles must separate from one another. And then the solute and solvent particles have to mix. Recall from chapter 13 that attractive forces exist between particles of all substances. Attractive forces exist between pure solute particles, between pure solvent particles, and between the solute and the solvent particles. When a solid solute is placed in a solvent, the solvent particles completely surround the surface of the solid solute. If the attractive forces between the solvent and solute particle are greater than the attractive forces holding the solute to itself, then the solvent particles pull the solute particles apart and surround them. These surrounded solute particles then move away from the solid solute out into the solution. The process of surrounding the solute particles with solvent particles is called solvation. Not salvation, solvation. To determine whether a solvent and a solute are alike, you must examine the bonding and the polarity of the particles, and then the intermolecular forces. So ultimately, how something dissolves is usually you've got bonds holding the solute together, And if the bonds between the solvent and the solute are going to be, or the forces between the solvent and the solute are stronger than the forces holding the solvent together, then the solvent can go around the solute, break it apart, and then surround it. Think like an amoeba. So aqueous solutions of ionic compounds. So in figure 15.2, you see a water molecule. We know water molecules are polar. They're dipoles. They have partially positive, partially negative ends. Water molecules are in constant motion because of the kinetic molecular theory. When a crystal of an ionic compound, such as sodium chloride, NaCl, table salt, is placed in a beaker of water, the water molecules collide with the surface of the crystal. The charged ends of the water molecules attract the positive sodium ions and the negative chlorine ions as well. So the negative side of the water molecule is attracting the positive sodium ions, and the positive side of the water molecule is attracting the negative chlorine ions. This attraction between the dipoles and the ions is greater than the attraction among the ions holding the salt together, and so the ions are going to break away and bond to the water. The water molecules then surround the ions, and the solvated ions move into the solution, as shown. There's a picture 15.3 on page 455. Solvation continues until the entire crystal has been dissolved, and the ions are distributed all throughout the solvent. So gypsum is a compound composed of calcium ions and sulfate ions. It's mixed with water to make plaster. Plaster is a mixture, it's not a solution. Gypsum is insoluble in water because the attractive forces among the ions and calcium sulfate are so strong that they cannot be overcome by the attractive forces produced by the water molecules. So solvation does not occur because then you have the bonds holding the ions together are stronger than the bonds between the solute and solvent. Okay? So aqueous solution. What about if it's not an ionic compound, though? What about if it's a molecular compound? So water can also be a good solvent for many molecular compounds, like table sugar. Table sugar is a molecular compound that could be sucrose or fructose or glucose, which is C6H12O6. So in any sugar, table sugar, for example, sucrose, which is C12H22O11, there's a lot of OH bonds, a lot of them. Sucrose molecules are polar because of those OH bonds. When water is added to sucrose, each OH bond becomes a site for hydrogen bonding with the water. And we know the hydrogen bonding is the strongest intermolecular force. So as soon as the sugar crystals contact the water molecules collide with the outer surface of the crystal. Then the attractive forces among the sucrose molecules are overcome by the attractive forces between the polar water molecule and the polar sucrose molecule. So it breaks apart. Sugar molecules leave the crystals because they're attracted to the water, and they become solvated. But then you've got oil. There's oil in figure 15.5, kind of from the oil spill, one of the bad oil spills. And oil is a substance made primarily of carbon and hydrogen, and it does not form a solution with water. Why? Why are oil and water immiscible? Because there's little attraction between the polar molecules and the polar water molecules and the non-polar oil molecules. So oil molecules are non-polar, so they're not going to be attracted to the water molecules, so they don't dissolve. However, oil spills can be cleaned up with a non-polar solvent. Non-polar solutes more readily dissolve in non-polar solvents. So oil doesn't dissolve in water, but oil does dissolve in other things. Okay? So let's talk about factors that affect the rate of solvation. As you just learned, solvation occurs only when and where the solute and solvent particles come into contact with each other. They have to be in contact. There are three ways to increase the collisions. Agitating the mixture, increasing the surface area of the solute, and increasing the temperature of the solvent. So agitating, stirring, shaking. Think about trying to dissolve something. When you shake it, it's going to dissolve faster. When you stir it, it's going to dissolve faster. Even like an ice cube, right? So that allows the particles to contact the surface more quickly, and therefore thereby allows new collisions between the solute and the solvent particles, which then increase the attractiveness, pull it apart. You get the idea. Without stirring or shaking, the solvated particles move away from contact areas slowly, but breaking it into smaller pieces would increase its surface area. So think about a lot of tiny ice cubes versus one big ice cube. The tiny ice cubes are going to just dissolve faster because they actually have more surface area relative to their mass. That's why a teaspoon of granulated sugar dissolves more quickly than a sugar cube. Raising the temperature also increases the kinetic energy, which means the particles are going to move faster and bounce around more, so they're going to have more collisions with greater energy. Okay? So there's three ways So 3 factors in rate of solvation. 1 is agitation, shaking, stirring. 2 is increased surface area. And 3 is increased temperature. Okay, so now let's talk about heat. During the process of solvation, the solute must separate into particles, right? Solvent particles also must move apart in order to allow solute particles to come between them. Energy is then required to overcome the attractions of the forces within the solutes and the solvent. So both steps are going to be endothermic because both steps require energy to happen, okay? So when solute and solvent particles mix, the particles attract each other and energy is released. This step in solvation is exothermic. So the overall energy that changes during the solution formation process is called the heat of solution. Okay, so we'll talk more about that later. Just know that's what it's called. Okay, so now let's talk about solubility. If you've ever added so much sugar to a sweetened beverage that the sugar crystals actually accumulate on the bottom, then you know that only a limited amount of solute can dissolve in a solvent in any given set of conditions, okay? If you ever put like Ovaltine in milk and you put a little bit too much, it's not going to all dissolve. You're going to have some sitting on the bottom, right? So solubility refers to the maximum amount of solute that will dissolve in a given amount of solvent at a specified temperature and pressure, okay? Because temperature and pressure can affect solubility. Okay, so solubility, the maximum amount of solute that will dissolve in a given amount of solvent at a given temperature and pressure. So as you can see from table 15.2, it gives you a lot of rates of solubility, and solubility is usually expressed in grams of solute per 100 grams of solvent, which is usually going to be like water, okay? So solubility is usually in grams of solute per 100 grams of solvent, which is very often water. Okay? So, I know this is kind of long, but we're almost there. Just as solvation can be understood at the particle level, so can solubility. When a solute is added to a solvent, solvent particles collide with the solute surface particles. Solute particles begin to mix randomly among the solvent particles. At first, the solute particles are going to be carried away. But as the number of solvated particles increases, that same random mixing is going to be more frequent collisions between solute and solute. So some colliding solute particles might actually rejoin the crystal or even recrystallize. And as solvation continues, the crystallization rate is going to increase in order to keep the solvation rate constant. So as long as the solvation rate is greater than crystallization rate, the net effect is going to be continuing solvation. So what does all that mean? Well, I believe that you can figure it out, but I will go through that a little bit more slowly. So as you have a crystal in the solvent, and the solvent particles are constantly colliding with the crystal, which is the solute, okay? So as this is happening, your solvent particles are being attracted to the particles in the crystal and pulling it away slowly. Now, as it's pulling it away, they're just moving randomly throughout. So some of those solvent, the crystal piece, some of the solute crystal pieces are actually going to bounce all the way out and back to the crystal. And some of them might actually recrystallize. But while they're recrystallizing, the solvent are still taking away more crystal particles. Okay? So as long as the solvent are taking away more crystal particles than the crystal particles are reforming, it's going to keep dissolving. But as soon as you get to the point where the crystal particles are reforming at the same rate that the solvent is pulling away the solute particles, it's going to stop dissolving. Okay? So that's rate of crystallization rate is the rate that the crystal is reforming, and the solvation rate is the rate at which it's dissolving. Okay? So depending on the amount of solute present, the rates of solvation and crystallization may eventually equalize. No more solutes going to dissolve. You're going to actually be in this state of dynamic equilibrium. So equilibrium means no net change, but dynamic means it's still moving. So you're still going to be solvating and you're still going to be crystallizing, but nothing's actually changing anymore. Although some particles will continue to dissolve and crystallize, in any solution that reaches equilibrium, the overall dissolved amount is going to remain constant. So that solution is said to be saturated. No more solute is going to be able to dissolve. It contains the maximum amount of dissolved solute for any amount of a given solvent at the specified temperature. Because obviously if you increase temperature, you can increase the amount that will dissolve. So that is versus unsaturated. Unsaturated is something where there's less dissolved solute for a given temperature than a saturated. More solute could be dissolved in an unsaturated solution. So what factors affect solubility? Well, one is temperature. Many substances are more soluble at high temperatures. So boiling, you can dissolve more sugar than if you just had a cup of water and tried to dissolve sugar. So for example, you even see a graph on page 458, figure 15.7. Calcium chloride, which is CaCl2, has a solubility of about 64 grams per 100 grams of water at 10 degrees Celsius. But if you increase the temperature to approximately 27 degrees Celsius, that increases the solubility up to 100 grams. So then you also, this fact is also illustrated by the data in table 15.2, where it gave you the kind of those same numbers. So you can look in almost every solution, KClO3, KCl, even NaCl, the solubility goes up as the temperature increases. The only exception is cesium sulfate. Okay? So as you can see from the graph and from the table, the gases oxygen and carbon dioxide are less soluble at high temperatures. This is a predictable trend for all gases. Why? Think about the kinetic energy of a gas. The kinetic energy of a gas is going to allow it to escape from a solution, and it's going to escape more at a high temperature because the gas particles are moving more quickly. So a supersaturated solution contains more dissolved solute than a saturated solution at the same temperature. So you can have saturated versus unsaturated, and then you can also have super saturated. So if a tiny amount of solute called a seed crystal is added to a supersaturated solution, the excess solute precipitates very quickly. So this is actually how you make rock candy. You supersaturate the solution, and then the seed crystal, the excess solute is going to precipitate onto the seed crystal, which makes the bigger crystal. So again, that's how you make rock candy. You supersaturate water with sugar. We tried it one year in chemistry. It didn't go that well, but you can do it on your own if you boil water and while it's boiling, mix in a lot of sugar, put in some string. You can find instructions on the internet. So using crystals of silver iodide to seed air supersaturated with water vapor cause water particles to form together, form droplets that fall to earth as rain. So rain actually comes from when the atmosphere is supersaturated. Cloud seeding. Rock candy as well. Pressure also affects solubility. Pressure affects the solubility of gaseous solutions in particular. The solubility of a gas in any solvent increases as the external pressure increases. So carbonated beverages, they depend on this, right? Carbon dioxide gas is what's dissolved in your carbonated beverage. That dissolved gas gives the beverage the fizz. In bottling the beverage, carbon dioxide is dissolved at a pressure higher than atmospheric pressure. When the beverage container is open, the pressure decreases, right? We know that. We open something that's carbonated and you hear the pressure decrease. That's why if you shake it, it's going to explode when you open it. When the beverage container is open, the pressure of the carbon dioxide gas in the space above the liquid decreases. So it's usually the pressure that's in that little bit of air at the top. As a result, the bubbles form in the solution, rise to the top, and then escape. Unless the cap is placed back on the bottle, the process will continue until it goes flat. That's why you have to cap your sodas. So let's talk about Henry's Law. And this is the last thing we'll talk about. The decreased solubility of the carbon dioxide contained in the beverage after the cap is removed can be described by Henry's Law. Henry's Law says that at any given temperature, the solubility of a gas in liquid is directly proportional to the pressure of the gas above the liquid. So what that looks like is S1 over P1 equals S2 over P2. It's a lot like some of the gas laws. You will often solve Henry's law for solubility at a new pressure. So for the most part, what you're not going to know is S2. You can also rearrange this equation to be S1 P2 equals P1 S2. You can also rearrange it if you really wanted for S2 equals S1 P2 over P1. Each one of these is the exact same equation. They're just written slightly different ways. Okay? So let's use it once. Let's solve one of them. And then you have 2 of these in your Junopod along with a couple of concept questions. So if 0.85 grams of a gas at 4 atmospheres of pressure dissolves in 1 liter of water at 25 degrees Celsius, how much will dissolve in 1 liter of water at 1 atmosphere of pressure and the same temperature? It's important the temperature can't change. If the temperature changes, we have a problem. So temperature is never going to change. So we know we were given S1, the solubility 1 equals 0.85 grams per liter. We know pressure 1 was 4 atm. We know that pressure 2 is 1 atm, and we're looking for solubility 2. So we can use this bottom version. Remember, they're all the same. So I'm going to erase these. Let's say we have S2 equals S1 P2 over P1. So S2 equals, we plug it in, S1 is 0.85 times P2 is 1 over P1 is 4. We solve that out. 0.85 times 1 is 0.85. 0.85 divided by 4 is 0.21 grams per liter. That's it. Plug and chug. All right? So you got 2 of those and then a couple concept questions in there. Good luck. I know that was an awfully long lesson with a lot of concepts, but hopefully you understood. I recommend also reading the book, following along, figuring it out. Get it a couple different ways. Read it, hear it, watch it, try it, all that stuff. Okay? Good luck. You guys can do this, and I will talk to you later. Bye.